Okay, thanks a lot for inviting me and for the opportunity to tell here bits of our story. I would like now to argue from a mostly research academia perspective why open source, so open science, open foundation models are very important to get the actual measurable progress in what we call transferable learning via deriving scaling laws and measuring the probably one of the most important properties of this models that come out from the training, namely generalization, and all the troubles that you can reveal when doing so. So arguably one of the most important breakthroughs so far that happened in our field in core machine learning is that we finally have a way to train models, to have learning procedures that allow for transfer across various conditions and tasks. So back then, before, I don't know, 12, maybe 10, here's the right date, we had a situation where if you would like to solve a task via data-driven machine learning, you collect quite a large data set. It has to be quite accurately labeled. You train something, but then this model is very task-specific, so you cannot really actually transfer it across tasks, and even within one task, it was rather fragile in how sensitive it is to changing the conditions of the task. So it was not reusable at all. You have to train each model for each task again and again. After 2012, we have a much better situation. Now we have a set of methods that then define learning procedure that we might call a generalist learning, where you pre-train once on a large, diverse data set, web scale. A data set might be a language vision. And then you can take this model and transfer it across very different downstream tasks under very different conditions. So now the question which is still open is how to systematically progress on the top of what we have. Because there are a lot of things that you can change in the learning procedure that will result in making it better, but because there are so many things to touch, what should you do? And how to compare your how to compare your attempts to one each other, so what to prefer to change in the learning procedure to make it more transferable, more scalable. So the foundation models have this very important property of exhibiting scaling laws, which means that if you, during the pre-training, without changing anything on the core algorithmic procedure, invest in increasing compute, data, scales, model size, you see for certain types of algorithms a steady improvement in important characteristics of the model that you obtain. So error rate on different downstream tasks that you consider to be standardized benchmarks, or what you might then call generalization if you consider your benchmarks to be broad enough and actually measure out of distribution generalization properly, so under this condition. So the scaling laws allow you to predict various important properties and function of the models by conducting experiments on much smaller scales, and then project, so the predictions are projected to the larger unseen scales, and the accuracy of these predictions depend on the way how you derive the scaling law. So if you do it right, you can have accurate predictions, and then you are not blind anymore in what your learning procedure would look like if you invest in these various scales during the pre-training. So it allows you to have a systematic way to say, I go to a particular scale, and then I will expect certain functionality and properties of my resulting model there. It also allows you, and here the very central part of the chinchilla paper from Hoffman et al., already quite some time, at NeurIPS 2022, where one of the approach to derive scaling laws allows you also to make predictions about the important properties for practitioners. So how many parameters, how many data samples, tokens you would have to take on a given scale, on a given compute budget that you have available to train a compute optimal model that gives you the best model performance. Following these predictions allows you to have a clear statement about the scale span that you would like to train your models on to obtain model artifacts of given predictable performance and properties as a model family across various scales. So scaling laws exist for very different types of foundation models, for learning procedures that do either pure vision or language vision, which I will talk a bit more in detail later. So here, for pure supervised vision scenario, VIT pre-training done by Google people, CVPR 2022, you also see that you can predict the properties of a vision model if confronting it with a large number of images. So before we were looking at language-only case. The problem is, though, was very severe a couple of years ago. Now it's getting a bit better. That in order to study scaling laws for important model types, for foundation model types, you need to have certain resources available, so compute resources, but also human resources, so people that are experts in these types of scaling law derivation experiments, and also experts in doing distributed training runs to have predictions confirmed on larger scales. And most of this research actually still happens in the few industry labs that are more or less closed, either totally closed like OpenAI or somewhat closed like Meta, Google, also Alibaba and friends on the Chinese side, usually releasing open weights artifacts at best, and then the data sets remains closed, which makes an inherent problem here of non-reproducibility. So as most of the properties of the scaling law are heavily affected by the data set, getting it closed makes actually scaling law studies impossible. So you cannot reproduce anything this way, except you try to guess how the data set look like, and if your guess is fortunate, then you might hit the right ingredients. If not, then you are tapping a bit blind there. So this situation led to rise of grassroots research communities that attempted to open source the whole pipeline, study foundation models and data sets required for their training. So Luther AI in US, appearing around 2020, 2021, concentrated on language, is still concentrated a lot of language studies. Pile as data set, Pythia as language family, also Lemma as a more specialized math language model. So big science in Europe and France that was heavily spearheaded by Hugging Face folks, dealt with language, code, language vision. So initially it was language, attempt to replicate GPT-3, resulting in Bloom and Roots, which unfortunately was not released fully, but it was a good initial attempt that gave hope to the community, followed then by a number of very useful artifacts like StarCoder, so IDFix multimodal, Flamingo replication, SmallLM right now, we have Lubna sitting there, this also goes in the direction of this whole pipeline being fully open, fully reproducible. So Lion appeared in Germany 2021. Important hub of Lion was from the start the Jülich Supercomputing Center of Helmholtz Association, where big machines are standing that allow these experiments. And from the start, Lion was focusing more on multimodal learning. So language vision, most prominently OpenClip, and the corresponding data sets like line 400M 5B, image text pairs data sets web scale that were gathered to conduct experiments on replicating closed OpenAI clip, which is still and was very important foundation model type, and leading to a number of other follow-ups like data comp, so data set, very data-centric track of composing data sets that lead to better pre-training. Open Assistant, so instruction fine-tuning data, CLAP, where Mariana was involved, sitting there heavily, language audio, Open Flamingo, that is similar to IDFX, and DCLM, now the new open source language model family that gave the dataset DCLM baseline that many people are using, including, how I heard at least, QN as well. So this now creates a landscape where open large data sets and foundation models are available, allowing the research to progress, being reproducible, and we have more and more disjoint efforts across institutions and organization boundaries that bind strong labs together. So the hallmark of this is the opening of the whole pipeline, so dataset composition, dataset itself, model training source code, model as an end artifact, and importantly, benchmarks and evaluation, often still a bit undervalued somehow. I have a feeling, maybe I'm wrong. So this evaluation and benchmarking to be reproducible and open and touched and common effort is very important. So on the example of Lion datasets and OpenClip, you have Lion as open data comp as a follow-up work, also having a dataset then released, which you can use to train OpenClip, OpenFlamingo, this kind of language vision models, and then we have also Mehdi sitting there, Clip benchmarks as a fully open, fully reproducible benchmark suite that everybody can use to evaluate these models in standardized manner. For the language, there are way more actors in place. As I mentioned, Hugging Face, LLRI, Allen Institute with Olmo, right? Together AI to some extent still, where you have data sets that are open, training routines that are open, and with a Lemma-Val harness, for instance, almost like an industry standard in evaluating these models. So that looks much better than a few years before. To give you some idea how this whole pipeline can be opened, I give an example of what I know the best, our work on OpenClip, training with image text Lion datasets and data comp datasets. So first thing you have to do is that you have to make sure that you get a web scale image text dataset in shape, and you cannot share it freely because it will land up in gray zone, and then you will have a lot of problems arguing how to share it freely across people. So the idea was then to instead collect metadata with links to the available images on public internet, and people have to use then fully open source pipelines to assemble these datasets together on their own. So this was work heavily driven also by Romain Abumont from Google. So you see also industry people are dragging along here and provide this open source repositories for the community to be used. So back then, it's already like, what, 3 years ago, we managed to collect a data set that was an English site, about 2.3 billion image text pairs, and in total it was 5 billion, so it was enough and still enough for the community to drive research experiments. And we would like to increase the scale, of course, there's difficulties bound to it, but having this 2 billion is surely enough to figure out what we can do better on the top of existing learning procedures. As a follow-up, we had the data comp 1B. That was then a more systematic procedure to extract from raw pools of common crawl available data subsets that result even in stronger pre-training. And here you have also a clear benefit of open data. When the troubles with the legal samples in Lion came up, we were able to react quite quickly in common effort with organizations that provided us hash lists to filter out the illegal samples, around 1,000 out of 5 billion, and create ReLion that was released September 2024 as a safety revision update so that Lion datasets can continue to be used in the research frame on and on. So getting the open data out, of course, gives you a null surface for the attack because nobody else doing it. But if you do it in open, then people come and also help you to fix the problems, like with software. So don't be too scared to attempt to release data openly. If you gather the right community around it, the problems with it will be also fixed in common effort. So importantly then, you can use such data sets to conduct experiments to derive scaling laws for the learning procedure of the interest. And here, learning procedure of interest is language vision, contrastive pre-training, so CLIP models, OpenCLIP as an open source implementation driven very heavily by our friends from Stanford and Berkeley, Ludwig Schmidt lab mostly. And together the data the open source training code open allows you to do this kind of a research fully reproducible. What you see then is a comparison here between orange, the Lion data set and OpenClip, and the blue, the original points from OpenAI with closed data that we cannot control, but we can at least plot it together as a scaling trend. So the scaling law is for Lion data. The blue is just scaling trend, not a scaling law. It was not derived in the original work there by OpenAI. For their closed model, and you can already have a kind of a comparison here that allows you to say for this particular downstream task zero-shot ImageNet classification, you have somewhat better scalability of whatever closed data was used for a clip on OpenAI side, making a statement about the two data sets. So this is like data set comparison. Everything else been fixed, you vary the data set, you get via the scaling law, not just for one single, whatever arbitrary reference point on some scale, but for the whole scale span, a consistent statement. So what is actually a data set that gives you a more scalable learning here? But you have to be careful. This is of course task dependent. If you look not in the classification, but on the retrieval, you see that the Lion data set is all of a sudden the stronger one. So this leaves you, of course, with a lot of open questions. So what would you do in order to then combine the benefits of the data sets that are here hinted to be different and on different tasks, so that you have one canonical data set that results in most scalable behavior for this algorithm. Another important feature here was that we as open source community, of course, are always having to fight with this gap between what we the model capabilities we release and what is happening on frontiers and closed labs. And there, for the first time, we had a hope that we can close this gap completely. So we saw that by using open data and open routines, we can actually produce the models that are matching or even beating the strong closed models from the frontier lab like OpenAI. So it's not just a scaling law derivation that helps to do the science, but it's also a scaling law derivation that shows you that you can actually target strong models that are fully open. So there is no contradiction between open source and model capabilities being strong, so you can do it. It's hard, but it's possible. Another example like this is now DataComp DCLM, a model family. We did the same kind of a story without deriving full scaling law though for language only training, which also allows you a comparison. So if these are not full scaling laws, these are scaling trends, and then by plotting points across the same compute scale on the X, you can see the trends for the different models being here different mostly in the data sets. I mean, there are some other small bits that are different. So you can basically also then again start to think about which of the current data sets you would like to take in order to get the most scalable learning procedure out of it. And in general, how much time do I have? Okay. So, and in general, you see that scaling law derivation is a very powerful tool to allow systematic model comparison, data set comparison, and in general, learning procedure comparison. So instead of going to, again, arbitrary reference single point scale, and then obtain some numbers there for your learning procedure and say, okay, look, this is the number and this is another number. Maybe I'm better, maybe I'm matching, who knows what happens. You have here a trend that spreads across a scaling span. And this gives you a much better way to tell whether your procedure is indeed matching better or worse than another one. So here, as an example, in somewhat hypothetical, orange and blue, imagine there are just now two learning procedures, 1 and 2, and we can either compare model 1 versus model 2 while fixing the same open data. So imagine the data set is the same and we'll vary something on the model architecture side, or just some part of the learning procedure. Or you can do the other way around. You can fix the learning procedure, so open the model architecture, and vary the data set like I was showing before. So, and what you get out of it here is that you are not falling into the illusion looking at the somewhat smaller scales where you see, if you look at the smaller compute, the orange is definitely having a large gap, large offset. But if you would look a bit further, and not even at the larger scale here, so the scales here are still modest, so 10 power to 21 flops is not something that would make you suffer a lot. You can identify this crossing point, which would tell you that on the larger scales where actually the interesting strong performance lies, you would prefer the orange one. So the scaling law derivation helps you actually to see the full picture instead of just a short glimpse that can be completely deceptive. And this is a bit of exemplification. It's just a zoom of the previous plot. Zoom of the previous plot that was indicating, okay, orange is to be preferred on the larger scale. So if you would do the same experiments, not spanning a scale span wide enough, then you could have an entirely different decision that would mislead you. You would prefer the blue one. So you see the coefficient. Of course, if you look at the scaling coefficients, you realize, okay, that the orange one has a larger, and because it's negative, smaller, but larger in absolute magnitude, and you should prefer this method. But this is just zoom that takes into account all the points further on. So if we would not take them into account, not measure it, we would have almost parallel lines that would make your decision about what procedure is actually to prefer go wrong. So without open data and without the whole pipeline being open, you cannot actually do such studies at all. So the model comparison, dataset comparison is locked for you. That's why I'm strongly arguing that for the academic track, we need such open whole pipelines to make actually progress, so to make controlled progress in how to improve the current learning methods. And this becomes even more important if you think about the current trend of taking the pre-trained components and putting them into larger systems that reuse this language vision, say clip, pre-trained models and language components further on. And then you would like also to understand for the larger model, like here the foundation model for robotics, vision, language, action model, what is the combination on components, on which scales should you put in there? So if you cannot control for the data that went into the pre-training, you can hardly study it in systematic manner. You will be again blindly combining the components and hoping that something strong comes out. But if you would like to systematically improve, then you would have to keep this whole pipeline open, including the data sets for the first stage pre-training. So long-term goal of this, also scaling law derivation as an instrument, is to improve open foundation model scalability and provide this open, strongly transferable generalist models as basis for basic research that then improves on and on and on using this scaling law derivation method. For this, we require, though, of course, the benchmarks to be measuring the right quantities we are interested in. So we are interested mostly in generalization for the base models. How well do they transfer? And often we have comparisons of this kind that are reported in the current research papers, where you have a number of benchmarks that are more or less standardized, and then you evaluate the scores on those. So now for the reasoning models, different type of math or coding benchmarks, and then you would like to trust that this scores reflect some underlying core capabilities of the models well enough. The question is, of course, whether running the pre-training experiments and measuring the model capability also in early training stages gives you the right signal to decide, are you doing the right thing or not? So also in the scaling law derivation experiments. We have some evidence, this is our iClear work recently published, that you can predict quite well the performance on the downstream tasks from just a standard validation loss on reference datasets like C4. This is somewhat surprising because the community was having actually contradictory evidence that it's hard to predict from the upstream loss downstream task performance. But this is not the major trouble. So the major trouble is indeed that the benchmarks, the standardized benchmarks themselves that we take to measure, say, language model capabilities, seem to have some fundamental troubles with how the score reflects what the model can do. So one trouble originates from a very simple thing. If you have so-called poisoning of the training data with the test, then you immediately have illusion of your model performing strong, although the high scores are just having a very trivial explanation that something leaked from the test sets into the training data. And if training data is closed, you never know. There are methods that help you to identify whether something from your test is in the pre-training where you don't have access to the training data, but it's still hard to do. And there are a number of studies, two of them shown here. On the right, you see a very striking finding that if you measure the zero-shot, few-shot performance on certain benchmarks that contain the data set prior to the pre-training of a certain model, then you have a much higher performance than if you take the test data that was then released after the model was pre-trained, which gives you immediate a hint that something is strange, right? So if this measures intrinsic capability to generalize, then this should not vary. There was a very nice, a very ironic paper by Ryan Schaeffer from Illusory and other organs, I forgot, I think Stanford, or maybe I'm mistaken, that basically pre-training on tested is all you need to get this strong claim of capabilities. And actually the early releases of models like Phi by Microsoft were plagued by this, and maybe still is. And then who knows which other open weights models are having the same trouble. So this is what we wanted to test because we were curious actually how much of the capabilities that are indicated by these strong scores on standardized benchmarks are indeed there. And we constructed a very simple math text problem that is definitely below anything like, hard. So it's elementary basic school problem that kids can solve. And the way how we were attempting to measure generalization is that we were taking a fixed problem template and then just varying something natural in it, namely here the numbers. So you have the three variations of the same problem where the only difference is the numbers are varying. So, and I mean, if you trust the claim that is propagated by this high scores on standardized benchmarks that the models have strong capabilities, what would you expect from a model, Frontier's model, confronted with variations of this problem? I mean, my expectation was that it will be either solved close to 100% across variations, or if it's, I don't know, for whatever reason, cannot really solve it so well, it will be not fluctuating. So because you don't change anything about the problem but the numbers, the performance you observe should be flat, whether high or not high. And what we saw was surprisingly a very different story. So these bars are just correct response rates over 6 variations of this problem that I was showing you before. And you have really weird fluctuations. For some variations, it goes a bit higher up to 0.6. For others, it's going down almost close to 0. This is not something you expect from a model that, and this is GPT-4o Mini, not the strongest one, but it gets quite high scores on standardized benchmarks, also for reasoning. We looked then on a number of different models, including the strongest frontiers one, so GPT-4o, now not mini, GPT-4, Claude 3 Opus, back then they were strong. And you see exactly the same picture. So strangely, for the variation 4, okay, 4 brothers and 1 sister, you have almost 100% correct response rate for GPT-4. And then for the variation 3, there's just 4 sisters and 1 brother, it drops almost to 0. So something is off. We measured then across a large collection of models, seeing basically the same story. No matter how you design the prompt around this, whether it's thinking prompt or no thinking prompt, it's all the same. Some variations are going high up, some high down, although the problem structure stays. And then you have to see that this problem is very simple. We do not operate here in adversarial mode where we on intention do some hacks into the problem and it makes it complicated. Actually, we were helpful. We were trying to create a problem that is as natural as it is and formulated in natural language and go ahead. So we are still puzzled, and we tried to see whether we have some unfortunate hack in this problem. Maybe, you know, the models have some intrinsic incapability to deal with family structures, or they just parse it in a stupid way and then everything is collapsing. So we designed a set of control problems that have almost the same formulation as the original one, but have slightly different question and also, I guess, easier difficulty. So, and we see that these control formulations are all solved to 100% without any fluctuations by the models that entirely collapse on the other version. You can see actually the for Llama 3.8b, it already these control problems induce a performance drop, but funny-wise, this performance drop is happening in the flat regime. So if it drops the performance, it drops it across all variations equally. So there are no weird fluctuations there. So we wanted to have some demonstration why this might happen. So the original problem at the top with variations, and then we had a slightly different version that we call AW extended, where 2 entities are featured, Alice and Bob now, but the structure of the problem is almost the same. Yeah. So and what we did, so the reason why we introduced another problem was, just also to have a look what happens in slightly different modifications of it. But as a Claude 3.5, Sonnet was released last summer, it claimed very strong capabilities. It was beating whatever hell out of everybody on the benchmarks. And we saw that it actually solves the original problem without fluctuations. This is what you see in A and B plot parts there. So it kind of goes up everywhere on these 4 variations there where other models are. But then if we're confronted with a slightly different formulation of this problem, everything goes down. And the suspicion is that what I was presenting before is that you just have test leakage. So people take very similar problem. I mean, Alice in Wonderland problems were available for some months afterwards. Maybe it leaked into the data. Maybe it was synthetically generated given the seed of the similar problems. No idea. But you have here a situation where very similar problem types either is solved almost fully or it's collapsing all of a sudden. So this is not a generalization. Yeah, systems capable of strong generalization would not behave like this at all. So when we tried to replicate a bit in preliminary experiments how this can happen, so we fine-tuned Llama 3.1 8b on procedurally generated examples of the original AIW problem I was presenting before. And in A, it's a bit unfortunate here down there, you see that the original model cannot solve anything. So if you fine-tune on examples of the original problem, you see that the performance goes up across variations. Here, okay, you arguably have still fluctuation. Small-scale models are really broke. So one sees that also in these experiments that they cannot handle really things. It's a bit illusionary. So here already something breaks, but it goes up. I mean, compared to the 0, nothing. But then if you confront the same model that was fine-tuned now on the examples of the problem with this slightly different variant that I was showing you before, so compare it. So this is the original, this is the modification. Almost no difference. Then you see again hard breakdown. So This is, I think, what is usually happening in these cases. Some similar bits of problems are getting into the pre-training. It creates an illusion that models has capabilities that are robust, but they are not. So we were then interested what happens now with the strong reasoning models that are coming up as the next wave of models that can actually have a more robust capability, arguably. So we created then different sets of similar problems. Now here, going away from brothers and sisters, structurally it's almost the same. These are now male and female friends. The principle is the same. Fixed problem template, you vary the numbers. And we scanned a number of reasoning models, recent ones, including DeepSeek R1 and O3 Mini, O1 Preview. And we see that while in general the performance goes up on average, you still have these fluctuations, which is really strange. I mean, if you consider a reasoning model with a claim to solve Olympiad level, graduate level tasks, math tasks, hardcore, why does it have problems with variations of this simple problem? What is going on there? So we have our own efforts with in cooperation with Stanford and Berkeley called Open Thoughts. Here, this Open Thinker models, Open Thinker Llama 70B and Open Thinker Quent 32B is like distilled reasoning models, same like R1 people did it. And we see there, yeah, so the average response also goes down for our efforts to do so, but we still have fluctuations. So for the reasoning models, not everything is solved properly. And if you go to slightly harder problems, okay, this is now harder than before. So you have a lengthier formulation, and it's definitely not for kids, but it's definitely below Olympiad level, definitely below graduate level. This is still elementary school with a bit of pen and paper, you figure it out. And there you see that many of the reasoning models are also now going down in the average response rate. So these fluctuations are strong. Even O1 preview is beginning to go down. So I think there is a very clear discrepancy between the claims made by the scores on the standardized benchmarks and the actual capabilities that we observe. So we are interested in generalization here. So we would like to have flat response. If you present to the model a problem and create natural variations of it, a model with strong generalization should not create these fluctuations at all, and we don't see it happening. We see, though, that the reasoning model are clearly better than all the conventional large language models from the previous generation. So here's a bit of a plot that doesn't have this clear view on fluctuations, although you have the deviation bar that kind of hints how much spread you have. So the average rates are very low for all the conventional large language models, including DeepSeek V3 or the large Meta Llama 400B. And in the middle field, you see a lot of these distilled reasoning models. They have really a strong boost. If you pre-train, if you post-train on a bit of reasoning traces, that gives you immediately something. Yeah, this is clear. But it doesn't get rid of these fluctuations. As a conclusion, we have to be very careful in stating how strong the generalization capability is of current models that we train, and this has, of course, implications also for these procedures I was showing before in scaling law derivation. If you, of course, measure something that doesn't really reveal the properly the capability to generalize, then all your attempts to tweak the learning procedure towards a better state are a bit doomed. So we need better benchmarks that better measurement tools for generalization capability of the models. And so this long-term goal critically depends on these novel benchmarks being in place. So we need them, otherwise the progress will be a bit deceptive again. So now the final piece of my talk. Hopefully I managed to convince people that having all these components open is simply necessary for doing the proper science of transferable learning. Otherwise, you simply are tapping a bit in a landscape that you don't understand, and arbitrary things are happening there, so that would be not good. So this fully being the whole pipeline for building foundation models being open is a good thing for research, a necessary thing for research. example of such open pipelines exists. So I hope it's encouraging for people to follow the examples by Illusory, by Lion, by Hugging Face, to do this whole pipelines in this open shape. And then actually it's a win-win situation. We can reuse this for each other's research, and also industry, I guess, benefits a lot by operating on already validated components. This, though, requires a lot of resources for research and for maintaining such artifacts, so we need supercomputers available. Hopefully, public institutions will make these resources more and more available for people who do open source and open science. Also, to avoid replication of the same expensive measurements, we should figure out how to coordinate such expensive experiments better that are of common interest. So Lion has some experience in applying for publicly funded supercomputers with all problems bound to it. So these machines are still not maintained well. People sitting there have often no connection to machine learning community at all. They don't know how to get machine in the right mode. Then a whole load is coming to you to help people to get it right, but you know, this takes time. So here some common action is would be good if knowledgeable people come to these machines and make them livable, and then actually benefit from the compute available, because EuroHPC actually have something to offer. In our experience so far, the supercomputers in the EU are becoming actually hubs for large-scale basic AI research. So with all the problems still attached to there, and this is a good development. So I think it really then makes this open science for advancing strong open foundation models together possible. In Europe, we will have now some exascale machines. So the old Joules booster that is standing in Jülich Supercomputing Center will be replaced by Jupiter that has 24,000 H100s. And I think binding efforts together to use this compute for training important class types of open foundation models is a good thing to try. To put it into relation, let's imagine a moonshot attempt. You would like to have a strong open multimodal foundation model family, so maybe on the level of at least QNVL. This will require a dedicated large-scale compute, even to do basic research on it. Big science bloom times were, back then they got a dedicated partition on Jean-Zay, and back then 480 GPUs, extension of it was made possible by French government, and I think this is the way to go. I mean, this is not the number we can be happy with now, but if correcting for the situation now, we need a couple of thousands GPUs on each of this machine being dedicated partition for dealing with basic research and open foundation models. And then we can hope that in Europe we will indeed create a landscape that is strong enough to handle such artifacts. Otherwise, yeah, everybody will having their own fragmented efforts, and we will be lagging behind, and nothing will happen. So I hope the decision makers in the EU understand this. So we make some attempts to create alliances like this Open Source Foundation Models and Datasets Alliance, OSFOMO, where we would like to put under one hood people to coordinate resource acquisition for open source foundation models and datasets research. So it should be driven, of course, by knowledgeable people, by organs with strong track of record, researching and building these models. Hugging Face, Together AI, Loader AI, Lion. Hopefully we can come together, write common grants, decide what are the most heavily priority trainings one would like to do on it, and then using these resources for further progress. We have already now some large European projects dedicated to pushing it forward. So Open Euro LLM started only 1 month ago. Minerva and dedicated effort to build AI service centers in Europe as well. So we, as Lion, trying to support this with our friends from ELIS and from HPLT. Hopefully we manage also then to get interested people for pushing this together. So we are also hiring multiple full research positions to join across different centers, also in our center working with Lion at the Jülich Supercomputing Center in Germany. We have flexible remote positions. So if you have some interest in helping out on this, because we desperately need strong people, please ping us. To wrap up, acknowledgements go to all the people who are actually core researchers in Lion and friends. Dr. Mehdi Cherti is sitting there and probably coding something. Mariana, please talk to them. Ludwig Schmidt, one of our core main collaborators, a very strong person, is sitting in Stanford. Let's make this push in Europe happen. Ping us if you are interested to work together and join our Lion Discord server to exchange a bit. Thanks for your attention.